Hello, this is Brian Merrill with Jenny Elsner in our Austin office. Mark Chauvin out of our Minneapolis office and I have put together this webinar to present some information on the SikaGrout 300PT product in particular, and in general on grouting of post-tensioning concrete elements to help understand some of the background and the issues that have been happening in the last 2 or 3 years, and to provide some guidance for owners who are concerned about their post-tension elements. As I mentioned, the objectives of today's webinar are to understand a little bit of the purpose of the grouting in post-tension structures. We'll present a little bit on the history and the nature of the problems associated with the Sika 300PT. Mark will also provide some information on work done to date to address the significance of these problems, and then we'll also cover some of the changes in the post-tensioning industry that have been brought about as a result of these problems and the issues going forward. So I'm going to start with the purpose and use of grout in post-tension construction, talking about primarily bridge tendons, internal and external tendons, and then some history on the grouting process itself. There are really two purposes of grout in a post-tension structure, and my background is primarily in bridge construction, and so I'm very familiar with those applications, but it's very similar applications in building or other types of construction using post-tensioned elements. The primary purpose of the grout is corrosion protection of the tendons, and then a secondary but equally important purpose of the grout in some structures is bond. And so in the picture you see here is what's called a balanced cantilevered precast segmental bridge, and each of those concrete segments are actually glued together with an epoxy, and then they're really held together by the post-tensioning tendons. And so the bond of those tendons to those precast elements is extremely critical to make sure that you achieve the crack control that's necessary. You do not want to let a post-tension structure crack. That allows chlorides and other moisture and other deleterious elements to get in there and really do some harm to the post-tensioning system. The corrosion protection component of the grout, there are 3 levels of protection of a post-tension tendon, and the first one primarily is the concrete surrounding the tendon. And so in this diagram we've tried to illustrate these 3 levels. So the second level of protection, or layer of protection if you will, would be the duct. Nowadays we use the plastic ducts. In earlier years a corrugated metal duct was used, but the plastic has been shown to be more robust, have better leak control, and does a better job protecting the tendons. And then finally the third layer of the protection system is the grout itself. Now in this diagram we've intentionally biased the locations of the strands, as they would be in a real structure, towards one side or the other of the duct. As the duct profile or direction changes, those strands orient themselves to one side or other of the duct. And so you can see that while the grout, it does surround them, there are locations where the grout may not completely surround the strands to provide that protection. I mentioned earlier that my background is in bridge construction, and there are really 2 types of tendons used in the large bridge structures. There's internal and external tendons, and we'll discuss what those are in a slide or 2. And then I've shown also here the variety of tendon sizes that are primarily used on bridge structures, and you can see also there the jacking force used for those tendons, and you can see we're dealing with extremely large forces. That 37 strand 0.6-inch diameter tendon at the very bottom, that's a jacking force of 1.6 million pounds. And so there's a tremendous force in these tendons to hold up these bridge structures. I mentioned the 2 types of tendons, the internal versus the external, and we'll try to explain the differences between those 2. The internal tendons are bonded for the full length of the structure. They're primarily used in the balanced cantilever segmental type bridges. They're also used in the cast-in-place box girder bridges. Straddle caps, and I'll show you a picture of one later in the presentation, use internal tendons. And then from an inspection standpoint, so from an owner's perspective, they are much more difficult to inspect in service. These tendons are usually fully encased in the concrete, and so getting access to them can be quite difficult. The external tendons are bonded or attached to the structure primarily at discrete locations. They're primarily used for the span-by-span type segmental bridges. The early generation cable stays that are grouted current cable stays are no longer grouted, but the early generation could also be considered an external tendon. They're also very commonly used for retrofits. And from an owner's perspective, they do provide much easier in-surface inspection because the tendons are not encased in concrete, and so access is typically much more easily accomplished. So this is a kind of a cutaway of a typical segmental bridge or a box girder type bridge, showing the external tendons in blue located inside that void structure, and then the internal tendons encased in some portion of the concrete structure itself. And then these slides all show various stages of construction using internal tendons. You can see on the lower left and upper right the large volume of tendons that are going to be encased in that concrete element. The top left, you can see the holes across that top flange or top slab for the internal tendons on that balanced cantilever bridge. And then on the bottom right is a precast box girder bridge, multi-cell box girder bridge, and you can see every one of those anchors is an internal tendon anchor. And that also illustrates one of the concerns with internal tendons. While they are very well protected through the length of the structure, they are typically exposed at the ends or expansion joints of the structure where the tendons terminate. And so that's always been a point of concern within the industry. External tendons, though, as I mentioned, attach to the structure at discrete points, and that would be illustrated on the lower right of the slide, where you really, at the stressing anchorage and at the deviation saddles, that's the only point where the tendon connects to the structure itself. The two slides on the left are shots inside the box of segmental bridges. You can see those external tendons. And then, of course, the top right picture is a retrofit using external tendons as well. As far as grouting history, tendons have been grouted for a long, long time. Prior to 1999, though, the primary grout mix was simply cement and water, and then occasionally an expanding admixture was used. And the theory behind the expanding admixture would be that it would fill the voids as the grout expanded, and you would not end up with any voids in the tendon. A 1999 study at the University of Texas and funded by Texas Department of Transportation, first of all, concluded that the expanding admixture didn't work very well at all. It did not expand as anticipated to fill voids, and so there were significant voids left behind. They also studied the use of fly ash for those grouts. They studied some corrosion inhibitors available at the time, and basically they concluded that the cement and water grout that had been used up to that time was very poor as a corrosion mitigation method. It did not perform well at all. So they recommended using fly ash in the grouts. They recommended removing that expanding admixture. And with regard to corrosion inhibitors, the corrosion inhibitors on the market at that time tended to perform less than desired as far as corrosion protection. The issue is related to dosage rate. Corrosion inhibitors are typically dosed based on concrete volumes, and when you introduce them into grout, they may not work as well, and in some cases they could actually accelerate corrosion. So at the time, they recommended against using corrosion inhibitors. So that research in part spurred the first generation of the high performance or thixotropic grouts around 2000, 2001. And so from the Sika product line, that would have been the original Sika CableGrout. And then the industry itself evolved, of course, as they typically do. And about the mid-2000s, the second generation of high-performance thixotropic grouts were introduced on the market. And so from the Sika product line, that would be now the SikaGrout 300PT. The PTI grout specs were also changing during this time period. The first PTI grout spec was issued in 2001. So prior to that, there really wasn't an industry standard grouting specification. And then it was followed very shortly by the second edition in 2003. And then the most recent edition, the 2012, has been out for a couple of years now, and it has addressed many of the lessons that have been learned over the years since the 2003 specs were issued. The grouts we're going to be talking about today, the Sika 300PT grout, was generally mixed and placed in accordance with the 2003 PTI specs. And so what we're going to do is we're going to cover a little bit of those grout properties that were in that specification. And the first one is this thixotropic action or behavior of the grout mixture. And this is the grout mixtures with these thixotropic action are very complicated materials They're fluid when they're stirred, but they gel or form a semi-solid when they're left to stand. Now they can re-liquefy when more energy is put back into them, so they're very interesting materials to work with. One of the nice properties of them, the gelling agents that are in there to achieve that thixotropic action, prohibit the grout from mixing as well with the water that might be trapped in the ducts, and so that's actually a good thing. They do have a very high flowability when they're still being mixed or stirred, and it does a very good job of filling the interstices between those individual wires on the strands. They have very low or no bleed, so that's bleed water, which is very common in concrete or cementitious products. They're not supposed to have any chlorides. They have very low permeability, and they're very stable from a volume standpoint. They don't shrink and they don't expand, and so very good properties from a grouting standpoint. Now I'm going to transition a little bit to the particular product we're talking about today, the SikaGrout 300PT. We'll cover specifications, which are Sika's specifications, some of their production issues and locations, and then performance issues. Once again, from the PTI 2003 specifications, these are some of the grout properties that were in that specification. The different colors I put on here to indicate various tests that are run in the field or during trial batching, and to explain the differences. So that total chloride's in red, and that's a very low percentage weight, 0.08% by weight of cement. That test is only run, at least in the 2003 specifications, when the initial trial batch was made. There was no requirement in the specifications at the time for subsequent testing for chlorides, and that's an issue that the 2012 specs are going to address. The three tests in black, the fine aggregate, the volume change, initial set and permeability, are all run, once again, during trial batching. They may be run by an owner to verify a lot of grout or a shipment of grout meets the specifications, but it's not normally a test that's run in the field every day or even on every project. The blue test, the bleed, the compressor strength, and fluidity, at that time were run in the field generally every day when grouting operations were conducted. This is a copy of a data sheet from the SikaGrout 300PT from about 2007. They revised it in 2012, and I've highlighted on here this bullet where they say it's sand-free, and the reason I highlighted that was a significant difference between the first generation and the second generation grout. The original first generation grout had a microfine silica sand in there as a filler, and I believe the reports were coming back to the manufacturers at the time that sand was causing damage or wear to the pumps and the mixers used to mix this grout. And so the second generation grouts produced by most of the manufacturers generally took out that microsilica sand. And this is the second page from that same data sheet. And so here Sika is actually saying that during their trial batch period or trial batch evaluations of their grout, they were at half the rate of the total chlorides allowed by PTI. And then once again, they say that there are no fine aggregates in the mix. Now, the reality is, though, there are still some inert fillers in this product, and it was a calcium carbonate inert filler, which was not actually called or characterized as an aggregate. It's more correctly characterized as a filler, but it was not reported on this data sheet. Sika produced both the original first generation CableGrout and the second generation SikaGrout 300PT at a number of facilities. The top three are facilities owned by Sika themselves, and you can see there the dates of their typical production for both of their products. The bottom five locations, the BMI, Elite, and the others, are all contracted producers for Sika. But you can see here the range of time periods for which they produced both products, and in particular what we're going to be talking about is the grout produced at their Marion, Ohio plant. And during that time period they were making the grout from 2001 through about 2010. They produced about 24 million pounds of grout, roughly 16 million pounds went into bridges. And from discussions in the industry, it appears at that time, during that time period, that Sika was the dominant grout producer in the PT market with well over 50% of the market share. So now we're going to get into some of the particular issues with the SikaGrout 300PT product, primarily the chloride content issue that you may have heard about, and then some other issues related to soft grout. In 2010, in September, the Texas Department of Transportation discovered elevated chlorides in grout in 2 different bridges, but the bridges used the same lot of grout. At that time, the Texas Department of Transportation Materials Lab performed the scanning electron and energy dispersive spectroscopy, the ion chromatography, and the X-ray fluorescence on those grouts. They were also able to test some unused bags of grout that had been left over on the project, and did determine that there were high chlorides contained in the bags from one lot of grout, but the second lot of grout that apparently came from a different plant did not have any chlorides. At that time, they also noted some soft grout was formed, and I'll show you a slide of what that looks like. And at the time, they thought that was a secondary issue. Those samples were also sent to Sika's lab, and they did confirm those chloride test results. So this is what would be called bridge 0. This was the first bridge to actually determine that the chloride was contaminating the grout, bridge down on I-37 in the Gulf Coast region of Texas. It's a straddle cap, as I mentioned earlier in the program. You can see the slide on the left shows a straddle cap, and that black dash line shows the approximate location of the 5 tendons in that straddle cap. And on the right is a close-up of one of the tendons with the anchor cap removed. And you can see the lower half, the grout below that dark band is very hard, very dense, very solid, but it did have a 0.27% soluble chloride content based on weight of grout, not weight of cement. The top portion above the black band, you can see is very porous. It's actually very soft. It's clay-like or gelatinous in texture. You can remove it with your finger. Notice the extremely high soluble chloride content in that material. That's 2.13% by weight of grout, which is many, many times the specification limit. The black band in that grout was actually determined to be unreacted silica fume, which was one of the constituents of the grout mix. The left slide shows a spectral analysis of that soft grout, and I'm not a concrete or cement chemist, but the folks that are tell me that this signature, if you will, of that chemistry of that material is not at all what you would expect from normally hydrated, properly mixed cementitious materials. You can see the very high chlorides, the extremely high potassium, that's the letter K, relative to the lower calcium and silicon, which should be higher in this. And then on the picture on the right shows you just how easily that material can be removed and how soft it can be. Sika responded, and responded well, in our opinion. They hired SGH to help them evaluate the problem. Their primary interest at first was to investigate and develop repairs for the 2 Texas bridges. And during the course of that investigation, they were able to isolate the problem to their Marion, Ohio plant, and those products can be identified with the letter M at the end of the lot number on the bags. And then they further isolated the problem to the cement produced by the Boozy Unison cement plant in Indiana. They did check all of their other components of the grout and concluded that they did not contain any chlorides. In the process of doing this initial investigation, they also realized that they had shipped grout from this Marion, Ohio plant to many, many other projects. And so in addition to the repairs for the Texas bridges, they started a very large-scale testing program to help evaluate the issue nationwide. The FHWA was also notified by TxDOT about that time, and so in late November of 2011, King G, an FHWA administrator, issued basically a warning memo to the 50 states, just alerting them that there were some issues with the grout and they needed to be diligent in their inspection and testing of the materials. They also started their own testing program running parallel with that Sika was going to perform, to be conducted at Turner Fairbanks Laboratory headed by S.K. Lee. And then in February, a few months later of 2012, they issued a second grout memo. This provided an update on the testing conducted both by Sika and the FHWA and the sampling in progress. They then requested from the states a list of suspected affected bridges that may have used that SikaGrout product. And then they did recommend at that time that the states actually perform chloride testing for each lot of grout received. And that was something that had not been done typically to that point. And then finally, about a year after the first, or 2 years after the first memo, they issued this technical advisory that now gave results of the testing and a protocol for evaluating the level of risk and follow-up actions for bridges, but this can also be applied to other post-tension structures as well. And then in conjunction with that, FHWA and Sika published a catalog of projects where they suspect the high chloride contaminated grouts went to. And so you can do that search on the FHWA website and it'll pull up the catalog for all the states where they suspect they ship grouts. So how big is the problem? Well, Sika in that catalog identified over 200 specific projects using the Marion, Ohio grout. And that affects roughly 120 or more bridges around the country. They do have records that they ship grout to approximately 39 or more states. One of the issues is that it is a little bit difficult to track the product just because Sika's business practice is they ship some of their product directly to projects, but they ship other products to third-party vendors, contractor supply houses, if you will, or stores, if you will, who keep the product on the shelf for a period of time and then might parcel out smaller lots of grout to specific projects that don't need a large volume of grout. And so once that product leaves Sika's warehouse and goes to a third-party distributor, it's almost impossible at that point for Sika to track it. And in particular, the grout that was shipped to Texas, Sika had no records of that grout lot going to Texas. It actually went to California and then at some point was brought to Texas by a different contractor. This slide was produced by Sika based on the testing they did on what they call retains. So in general grout production, they have a retain sample that they keep for a period of time. In addition to the retains, SGH, who was hired by Sika to help with their investigation, actually went out and took some samples of certain bridges to try to characterize certain production time periods. And so you can see from January of 02 to roughly January of 10, all of the test results that Sika has provided. And the dashed red line there shows the specification limit. So you can see the significant number of test results that are above the specification limit for chloride content. And in particular, the oval at the top was just to make sure you noticed that there was one of them that was extremely high grout content. The little red box was the bridge in Texas that the first chlorides were noted. So based on this, the FHWA came up with recommended chloride values for evaluation if you didn't know the exact lot number of your grout. And so basically they've tied this to production period. So on the left, if your grout was installed between, let's say in 2007, and you don't know the lot number, the default chloride value for a risk analysis would be 0.43% by weight of cement. And that's based on those field samples. And so they took basically the highest level chlorides tested for the 2,000-year period and put that as the default chloride value, which is a conservative way of approaching this problem. During the course of this investigation, there were some issues that were brought forward to the industry related to quality control, grout production, and specifications. One of those is that, as I mentioned earlier, that the PTI grout specs in place at this time, the 2003 version, did not require recurrent chloride testing. It was only required during the initial batch design. So the 2012 specs now requires a chloride test on every production lot of grout so that you will get recurrent chloride testing. In addition, the traditional cement used for grout, which is an ASTM C150 cement, That ASTM C150 specification does not require chloride testing of the cement, and in fact there are no limits for chloride in cement in that specification. And that has not yet been addressed to my knowledge. It also was apparent to those of us in the industry and that Sika and possibly other grout suppliers may not have had an effective QC program for their materials received processes. And I do understand that those grout producers now are aware of this issue and are testing their received products, the constituents that they use to produce the grout. And then in addition to that, the standard practice for many DOTs was that they weren't doing chloride testing in the field. They were taking manufacturer certifications that it contained no chlorides as good enough. And so that practice has also changed in recent times. I mentioned earlier the soft grout, and it was initially thought to be a secondary issue. We now know a lot more about the soft grout issue. The photo at right is actually soft grout, not as a result of a Sika product. It was a different grout supplier, but once again, it did form soft grout. What we have learned so far is that the soft grout can be highly corrosive, and I put the corrosive in quotes because it's not the traditional corrosion that you might normally associate with chlorides. This soft grout, as that spectral analysis I showed earlier, is very high in sulfates, and apparently when you get a high sulfate concentration, it actually prevents the normal passivation of the steel that would occur due to the high pH of the cementitious material. And so you end up with steel that crosses this interface from the hardened grout to the soft grout being very well passivated on one side and unpassivated on the other, and that leaves the steel extremely exposed for corrosion without regard to the presence of chlorides. There are some theories as to what causes the soft grout to form. We know from testing that if the grout exceeds the shelf life, those dry powdered admixtures that are included in the grout that give it those really nice properties tend to lose their effectiveness, and you can get some irregularities in the mixed grout that can produce this soft grout. We also have determined that excess water, whether it's mixed in or maybe it's in the bottom of the pump or the bottom of the mixer that might get introduced into the grout, can also help produce the soft grout. There is a suspicion that the fillers, the calcium carbonates that are used in lieu of the really fine sand aggregates, may help produce this soft grout through some type of filtering or clumping as the grout is pumped through the tendons. And then there's also the assumption that poor storage or installation procedures can also result in soft grout formation. So the 2012 PTI specifications do try to address all of these, and it is a much better specification for grouting procedures and practices. And so we think going forward that largely the soft grout issue has been addressed and corrected, but there is a period of time where soft grout was produced. And there have been some tendon failures attributed solely to the soft grout. There was a significant bridge in the Florida area built in 2003, and they actually had to do some tendon retrofits during construction, and it was those retrofitted external post-tension tendons that failed. And the slide on the right shows you one of those post-tension tendons and the failure that occurred. They actually found one that had completely failed, and a subsequent investigation found 15 others with corrosion. The failure they determined or concluded was due to corrosion, and it did use the SikaGrout 300PT, but there were no chlorides in the grout. They did find significant quantities of soft or segregated grout, and they found large voids in the tendons. And so in this case, the failure was attributed not to the chlorides, but to material and installation deficiencies that resulted in both the voids and the soft grout production. At this point, I'm going to turn over to Mark out of our Minneapolis office, and he's going to finish up with the investigation and fieldwork and involvement by WJE in the process.
All right, thanks, Brian. As Brian mentioned, my role in this webinar will be to review some of the fieldwork that's been done to investigate the SikaGrout 300PT chloride issue and some of the role that WJE has played in that work, and then also review some of the research that's been done to try to assess the significance of this problem. But we'll start with the field work. And the plan that Sika developed to try and assess the significance of the chloride issue was two-pronged. And the first prong was to build a database of all of the chloride content values that had been generated by the Marion, Ohio facility between 2002 and 2008. And that was done through testing of retains, and where there was not retained data available, through field sampling, collecting grout samples on existing bridges and testing them for chloride content. And then that information was supplemented with some information they received from the cement manufacturer that they believe is the source of the chloride contamination. And in total, the retain and field sampling as of last summer had captured 40% of the grout lots that were produced in Marion, Ohio during the time period in question. The other prong was to also determine the critical chloride threshold. At what level does the chloride content become a concern for corrosion? And that work involved a literature review of the work that had been done by others, and then a laboratory program of their own to supplement that information. So in terms of the database, the goal, again, was to collect samples from retains and field structures, and where the field samples were collected to make observations of the existing conditions. Was there any corrosion? Was there any soft grout? Any other issues of note? And to select the locations for field sampling, there were several considerations. One was the spread of the production dates. In general, time periods where Sika did not have retained data available, those were favored to try and fill in the database. Also, when looking at particular bridge structures, the accessibility of the tendons was considered. External tendons are generally easier to extract a sample from than internal tendons, where you might be limited to working at anchorages, if at all. There were certain critical grout lots that, based on retained data, they were known to have very high chloride contents. Those were targeted, and then certain critical structures where sampling was desired by bridge owners were also considered. And so, as a result of the consideration process and the evaluation of retained data, 12 bridges were targeted for sampling by Sika. 3 of those bridges were located in Minnesota, and they're identified as Bridge A, Bridge B, and Bridge C, all constructed during different time frames, 2003 to 2006 for Bridge A, 2008 for Bridge B, and then 2008 into 2009 for Bridge C. And the Bridge C project is actually a collection of multiple bridges, one of which was known to contain the grout lot with the highest known chloride content per Sika's retained testing. It was 0.56% by weight of cement. And WJE was fortunate enough to be retained by MnDOT to participate in some of the field sampling in Minnesota. The field sampling process involved 3 phases. The first phase was the planning phase, and MnDOT engaged the bridge designers of the 3 structures to review construction records and review the design of the bridges to first locate the grout lots on the structure, in other words, which tendons had which grout lot, and then to suggest tendons to sample. And based on that information, Sika developed a sampling plan on how they proposed to collect and repair the tendons, collect samples and then implement repairs, and also the number of samples to collect, both in total and then of each specific grout lot. And WJE was asked to review and comment on these plans. Once agreement was reached, we progressed to the field work. Access to the structures was provided by MnDOT. DSI and VSL were engaged to provide contractor support for opening the tendons and collecting samples and then implementing repairs. And Sika, SGH, and WJE worked in parallel in the field to collect samples for laboratory testing and to make observations. Once we had our samples, they were submitted to the lab for acid-soluble chloride content testing, and the results were reported and shared. So the field work, as mentioned, generally involved opening external tendons and anchorages. External tendons were preferred because it was much quicker to open them up and get a sample out, also much easier to repair. And a sample opening of an external tendon is shown in the photo in the lower left. At certain bridges where external tendons were not present, or for other considerations, occasionally certain grout lots were accessed at the anchorages, which the photo in the upper right reflects, where a certain amount of the pour back was removed to expose the plastic grout cap. The grout cap was cut and grout was removed, and then everything was put back together. And so through the sampling process on all three bridges, what we found was essentially no concerns. There was no corrosion at any location, no soft or segregated grout at any location, no voids, and no grouting issues. Everything looked good. And although we were not involved with the other 9 bridges that were targeted for field sampling, the same conditions have been reported at those bridges to the best of my understanding. In terms of the lab testing, as mentioned, we collected a number of samples and they were submitted for acid-soluble chloride content testing. Bridge A, which has approximately 500,000 pounds of SikaGrout 300PT in it, consisting of 17 different lots. 5 of those grout lots were targeted for sampling, and in all cases, the chloride content was less than the PTI specified limit of 0.08% by weight of cement. Bridge B, built in 2008, has a little over 2 million pounds of SikaGrout 300PT and 13 distinct grout lots. 12 of those grout lots were sampled, and the vast majority exceeded the PTI specified limit of 0.08% by weight of cement, with approximately 1/4 to 30% exceeding 0.2% by weight of cement, or 2.5 times the PTI specified limit. Bridge C, built a year later in 2009, has only a limited amount of SikaGrout 300PT in it, although that number I'm not sure is confirmed. We attempted to target one grout lot for sampling, the one that was known to be in excess of 0.5% by weight of cement. Grout lot records were reviewed to identify where we thought, which tendons we thought the grout lot was present, and it turned out that we ended up sampling 2 different grout lots. We attempted to take 2 samples of the same grout lot, the one that was in excess of 0.5%. We ended up getting 2 different grout lots, one that was at approximately 0.13% and one that was around 0.35%. So both exceeded the PTI specified limit. One exceeded 0.2% by weight of cement, but neither was the 0.5% grout lot that had been targeted. And in that case, for that particular structure, the difficulty in locating the grout lot was really related to the grouting records during construction and not the information from Sika. We know the grout lot is present in the bridge, but unfortunately there was insufficient detail in the grouting records to pinpoint exactly which tendons contain that grout lot. So going back to the graph that Brian showed previously, again, the chloride contents that were captured at Bridge A were all less than the PTI specified limit, which is the lower black line, and those data points are kind of captured in the green box on the left, generally low chloride content. As we move further along in the Marion, Ohio timeline, there gets to be more variability and certainly higher chloride contents, and many of those were captured through the sampling that was done at Bridge B and Bridge C. So on somewhat of a side note, there were 4 things that I found interesting associated with the field sampling work that was done on the 3 bridges in Minnesota. The first is initially there was an effort to better define how many samples to take and where to take the samples, in other words, which grout lots to target. In the field, an initial sample was taken of a particular grout lot, and an instrument called the rapid chloride test was used. Essentially, the powder is mixed with a solution and shaken up for about 5 minutes, and a chloride content is measured. And although the instrument is represented as being very accurate, what we found was that it was very inaccurate. And part of the issue may have been, at least initially, part of the issue may have been the time of sampling. We were collecting samples when it was extremely cold, and so some of the erroneous results were believed to be related to that. However, some changes were made to that process, and the RCT tests were run in hotel rooms at the end of each day, and we still found the same inaccuracies. And so unfortunately, that test just was not a reliable indicator of what sort of chloride content we would expect to get. So it was dropped from the program. But in the event the test is considered for other kind of quick and dirty chloride content analysis, I would have some hesitation about that, at least based on my experiences and the results we obtained in some of the field sampling work here, particularly with respect to SikaGrout and its chloride content. In addition, in terms of chloride content, at the start of the field sampling program, there was some discussion on what is the proper chloride test to run. There was a thinking on the part of Sika that because we were sampling bridge structures, that the AASHTO chloride test would be appropriate, which is AASHTO T270. And that test involves chloride analysis of a 3-gram sample. And through some internal discussions with the folks in our Janney Technical Center, it became pretty apparent to me pretty quickly that although a fine test, the AASHTO T270 test will lead to much more variable results. It's just simply not as accurate as the ASTM C1152 test. And so there was some back and forth on what the appropriate test to run was because of that. And one of the, I would say, convincing factors was that PTI, ACI, and even AASHTO all recommend ASTM C1152 as the proper test for performing acid-soluble chloride content testing. So in effect, AASHTO doesn't even like their own test, and it was just something that simply hadn't been checked before the field sampling. And in our opinion, would have been somewhat significant because particularly where we were comparing results, the more variability in those results and in the test procedure, or that the test procedure leads to variability, it just becomes more challenging to do. If that margin of error is higher, then comparing apples to apples just gets more complicated. So although AASHTO tests were run for the initial bridge that we sampled, they were dropped for the remaining bridges in favor of ASTM C1152. In addition, we also, on one of the bridges that were sampled, Bridge B, because we had a little extra sample, decided to run a water-soluble chloride content test in addition to the acid-soluble chloride content. And we tested several of the samples that were collected, and what we found was that only 27 to 39% of the total acid-soluble chloride content was water-soluble, which I think was somewhat surprising and certainly lower than the fraction that we expected. And the last nugget is, what were they testing? And that is it with respect to Bridge B, because as Brian mentioned, chloride content testing was not typical during the field or during construction of certain bridges. However, for Bridge B, all 13 of the grout lots that were supplied on that project were shipped off prior to construction for laboratory testing of chloride content to verify the information on the datasheet. And all of the values, all of the grout lots tested out at negligible chloride content, less than 0.011% by weight of cement. Now, in 2012, we tested 12 of those grout lots, and as the previous slide noted, 86% of them were in excess of 0.08% by weight of cement. So clearly, there's an issue here, whether the data was reported erroneously or perhaps clearly there's a disconnect. What had been reported to have no chloride, in fact, did have chloride. So that kind of summarizes the field work, and now we can take a look at some of the research that is ongoing to try and assess the significance of the problem. In terms of the chloride content and the chloride threshold, PTI, as Brian mentioned, specifies a chloride limit of 0.08% by weight of cement. However, there's little agreement on how much chloride it takes to initiate corrosion. There has been a lot of research done, and in general, the findings are all over the board. ACI 222 has reported that the chloride content threshold for unstressed strand may be as high as 1.2%, and WJE has done some research in the area and found similar numbers, maybe even up to 1.4%. In general, the chloride content threshold for strand has been found to be higher than that for reinforcing steel. And although it's not exactly clear why that is, some of the factors that have been cited are the material or the manufacture of the strand, the smooth surface of the strand, possibly the drawing oils. All of those things may contribute to a higher threshold for corrosion. However, there's not nearly as much research for strand in grout as there is for strand in concrete. So this is a graph that was put together by the Federal Highway, plotting out the chloride content thresholds that have been reported by researchers since 1975. And the two highlighted numbers are the work that I mentioned done by WJE in 1987, Don Pfeiffer and others, with the little bubble on the left representing reinforcing steel and concrete, where the chloride content threshold was found to be 0.17 to 0.26, and the larger bubble on the right being strand in concrete, where, as I noted, the chloride content threshold was as high as 1.2 to 1.4. And those results are not too different from what other researchers have reported, although some have found the chloride content threshold for strand to be as high as 2.2. Others have found it to be as low as 0.17. And in general, there's numbers all over the board for what is the chloride content threshold. As I mentioned, there's much less available information for strand or reinforcing steel in grout. And this graph was also put together by Federal Highway and reflects that collection of data that's available from 1986 through 2009. As you can see, some of the more recent research suggests that strand in grout may have a chloride threshold of even less than 0.01. The most recent work done by David Trejo of finding 0.006 to 0.018, those are well within PTI's specified limits. Others have found it may be as high as 3.08. So Federal Highway, as a result of their literature research, concluded essentially that strand that's placed in dry and high quality grout, where you have high pH and no chloride issues, no sulfates or anything like that, the chloride threshold may be as high as 1.5% by weight of cement. However, if that's not the case, if you have strand that's in certainly in soft grout, or if you do have voids, if there is recharge issues, anything like that, the chloride threshold may be as low as 0.01% by weight of cement. And so, to supplement all of this available information, Sika has instituted a research program. And the goal of the program was to determine the chloride threshold values that are cause for concern for corrosion. The program consists of single strand specimens, a 12-inch long piece that is dropped into a plastic tube and grouted. And the variables were the chloride content of the grout, whether or not there was a void in the sample. They modeled repair conditions where you have a high chloride grout on the bottom and a no chloride grout on top. In some samples, holes were drilled into the side of the plastic tube to increase oxygen availability, and then the water content of the grout was also varied. And all of these samples were stored within a conditioned cabinet that was generally kept hot and humid. Federal Highway is also doing research on the chloride content threshold, and their program is a little more ambitious, both in terms of the variables they're considering in the scope, but their goal is the same: determine the chloride threshold values that are cause for concern with respect to corrosion. They evaluated single wire specimens, single king wires, single strands, much like Sika's work, and then multi-strand specimens in somewhat of a mock-up assembly that is shown in the photograph on the right. The variables they looked at were also chloride level. Unlike Sika, they evaluated stressed versus unstressed conditions, again, to try and more accurately model an actual tendon. And there is some research that suggests that stressed strand will have a lower chloride or a lower corrosion threshold than unstressed strand. They also modeled voided specimens versus unvoided, and they evaluated the effects of recharge with certain voided specimens where water was introduced into the sample. And unlike Sika, Federal Highway is cycling the temperature and relative humidity conditions to more accurately model seasonal changes. And so some of the initial results that have been reported, Sika's research, there was some initial surface corrosion found in some of the samples that contained high chloride content, and I say high by 0.6% and above, with it being more noticeable, obviously, in the higher chloride samples. And these local corrosion conditions were generally at the point where the strand was in contact with the duct, and the theory was that the high chloride had retarded the pacification of the strand, particularly where it was not encapsulated in grout, and instead it was in contact with the plastic tube. Now, continued monitoring showed that this initial corrosion went dormant, and that region of the strand and the strand in general then repassivated. It was just a process that was retarded, particularly in that area where the strand was in contact with the tube. Federal Highway found some levels of pitting corrosion at lower chloride contents, as low as 0.4%. However, they noted that additional research was needed. It was not clear that that corrosion was sustained, and it may have been more of an initial corrosion phenomenon, somewhat similar to what Sika had observed in their testing. However, both researchers have reported that sustained corrosion occurred when the chloride content was at 0.75% or above. But unlike the chloride content issue, soft grout problems have been linked to tendon failures and corrosion problems on several existing bridges, and the problems manifested quite quickly. As Brian noted, multiple failed tendons were found on an 8-year-old bridge in Florida, and failed tendons have also been reported on a 2-year-old bridge, actually less than 2 years old, in Europe. In both cases, failure locations were correlated with regions of soft grout. Also, the formation of soft grout has been noted during or following construction on several bridges where SikaGrout 300PT was used, including bridges in Texas, as Brian mentioned, and several in Florida, including some product that I believe was not from the Marion, Ohio facility. Now, soft grout and segregation issues were not really the focus of the research work that has been performed to date by Sika and FHWA. Those studies focused more on the significance of elevated chloride levels. But research has been conducted by several others to investigate and evaluate the soft grout problems. That includes work sponsored by the Florida DOT and conducted by Dr. Lau at Florida International, Dr. Hamilton at the University of Florida, and Mario Paredes, the corrosion engineer at FDOT. In addition, research has been performed at Polimai in Italy by Luca Bertolini and Maddalena Carsana. The research performed by these individuals has been aimed at understanding the formation of soft grout, or kind of the how, why, when, and where it can appear, as well as the corrosion science and the risk assessment of the soft grout regions, or why rapid corrosion failures have been manifesting, and some findings have been published. In terms of the nature of the soft grout material, the research has found that it tends to occur at tendon high points on the top side of ducts as a result of segregation. Now, that's not unlike the normal segregation and bleed water problems that can manifest in PT tendons given certain conditions, particularly with traditional Portland cement grout mixtures. However, the regions of soft grout are different, and they're unlike the normal segregation and bleed water issues where the water may tend to evaporate or be reabsorbed, just leaving a grout void. Instead, the soft grout material forms, and it exhibits a tendency to stay in this wet plastic state, kind of resembling modeling clay, as Brian discussed, and the material stays wet or moist, much higher moisture content than the grout normally would exhibit. It also exhibits a different chemistry than the dry, harder grout that consolidates at the bottom of the duct, and that includes much higher sulfate content and high pH, particularly in the interstices between the wires where the oxygen availability is really low. and soft grout can form irrespective of the chloride content of the grout. In other words, this issue is different. It's not tied into or related to the chloride issues that we've previously discussed. It's a different issue. And in addition, although the segregation leads to these regions of soft grout, there is not necessarily a void that forms, nor does there need to be a void to have corrosion problems. Because in terms of the corrosion mechanism, it appears that the portions of the strands or wires within the soft grout material never passivate, potentially as a result of the very high sulfate content and despite the very high pH levels. The lack of passivation and the elevated moisture content of the soft grout material appears to create a very rapid corrosion cell, with the unpassivated strand or the wires that are in the soft grout area at the top of the duct. They serve as the anode, and they are corroded by all the rest of the strands, the same wires that are all electrically connected together and are down in the dry and hard grout toward the bottom of the duct or away from the high point. All of those strands become the cathode, and because the area of that cathode is much greater than the small section of strand or wire that's in the soft grout region, this corrosion can occur rather quickly. And in addition, the University of Florida has performed some research to attempt to understand the how and why of the soft grout formation. And what they found is that the prepackaged grout materials that contain inert fillers like SikaGrout 300PT and some others are susceptible to segregation and soft grout problems under certain conditions, much more susceptible than Portland cement grouts or other prepackaged grouts that don't contain inert fillers. And the pre-bagged grouts with fillers appear to have a much higher sensitivity to water content and product storage conditions, as well as certain tendon geometry considerations. And the addition of water to those prepackaged grout materials with fillers, either representing additional mixed water that was added intentionally or unintentionally, the research looked at 15% over the manufacturer's recommendations, or possibly water that's left in the tendon or the grouting equipment, again intentionally or unintentionally, consistently translated into the formation of soft grout. So when there's extra water there, or extra water in the prepackaged materials with fillers, soft grout was consistently produced. In addition, prolonged storage conditions, even when they were stored well, or poor storage conditions also translated into an increased rate of soft grout formation. Now, all of the tested grouts that the University of Florida looked at were new. In other words, none of them were the chloride-contaminated grouts produced in Marion, Ohio from 2003 to 2010 that we've previously discussed. And the results indicated that the susceptibility of the prepackaged grout products that were evaluated really varied by batch and facility, despite what I would assume is a similar product formulation within each batch and facility. It seemed to be much more random. And so, in summary, the chloride contamination issue is really more of a long-term durability concern. Corrosion problems would be expected to be much slower developing. And the nature of the problem is reasonably well defined. If Marion, Ohio grout exists in a bridge or a structure, the grout lot number or even the date of production or the date of construction should give us a sense of what the chloride content is or what the range may be. Or we could map the grout lots to certain tendons if grouting records are good, and then samples could be collected to get a hard number if desired. And in a sense, you can kind of figure out what you have and where you have it based on the information that should be available from construction, the age of the structure, hopefully good records. With all of that information in hand, you can kind of keep an eye on things and monitor for problems, particularly in areas of high risk or higher chloride. But the soft grout problem is trickier and more concerning, at least to me. It does not appear to be tied to a certain grout lot, a certain facility, or a certain date of production. Instead, it appears to be tied to these prepackaged materials with inert fillers, or at least there's a possibility that there may be soft grout if those products were used. And it appears to be a random problem that's related to the performance of the prepackaged grout products and the quality of the storage and the grouting operations that the product was used or subjected to during project construction. And if there were any issues and soft grout has formed and is now present, corrosion problems may manifest very, very rapidly. as has been observed already in Florida and Europe, much more rapidly than would be expected with the chloride issue. And because of the randomness of the soft grout formation, it is at a minimum possible that soft grout regions exist in the tendons of many bridges and structures, and we just don't know it. And I'm not really sure how we could find it because, again, the soft grout areas are not always or even very often associated with a grout void or something like that that might make detection a little less challenging. Instead, we're somewhat in the dark on both if it's present and if so, where it may be, unless there were reports of grouting problems or grout that did not set up or was otherwise not normal during construction, and those problems were documented in grouting logs or post-grouting inspection records. And there was one such instance at one of the bridges where we performed field work in Minnesota, Bridge C. Some supplemental field work was done on Bridge C because of that. During construction, there were some grouting records that indicated soft grout was present. Following grouting operations, borescope inspections were done, and in some of the tendons there was grout that just simply hadn't set up as it was expected to do. And initially it was attributed to cold weather, that the segments may have been moved outside a little too quickly and the grout just, the setting up process just kind of stopped. And so the segments were reheated for a while, and that seemed to help a little bit, but not as much as expected. So they were reheated for a little bit longer, and then everything seemed to be fine. But as a result of some of the issues that have come to light, MnDOT wanted to go back out and take some samples just to confirm that there was no soft grout present in these tendons where the issues had been noted back in 2008. And so WJE was again fortunate enough to be asked to go out and collect those samples and take a look. And similar to before, what we found was no problems, no corrosion, no soft grout issues, no voids. And we tested the grout. We opened up and looked at 4 of the 16 tendons, and we borescope inspected the other 12. They all looked good. At the 4 that we opened up, we collected some grout for sampling. It all had low chloride content. There was a little bit higher sulfate content than normal or than expected, but not alarmingly high, and it was a normal pH. So that kind of summarizes the field work and the lab work, but what's next? And I think future work is likely. 12 of the structures that have been identified as having the Marion, Ohio grout have been field sampled. That's really just a fraction of all of the bridges and structures that have it, and the focus has really been on just the bridges and not private structures, potentially parking garages or buildings that have the material present. And the bridges that do have, and buildings that do have higher chloride content, the range of 0.2% to 0.5% has been identified by Federal Highway as a somewhat higher risk, where much more frequent inspection or potentially even some form of monitoring has been suggested as potentially a way to kind of keep an eye on things and watch what's going on. Certainly additional research, I think, is likely. I believe the Florida DOT work is ongoing. I suspect the research done by Sika and Federal Highway will also continue, and certainly there may be many others that jump into it to try and get some more information. But on a side note, as I mentioned, many of the public and private structures have not had any field sampling done and have not really been the focus yet. One of those structures is one that was worked on by WJE. It was a retrofitted historic structure in California where we center cored and grouted to install some new reinforcing steel and some concrete pillars. And as a proposed substitution, SikaGrout 300PT was allowed to be used to grout that annular space between the new bar and the old concrete. And the work was done in February of 2009. Obviously at the time, unaware of any issues with the SikaGrout product. It's a sensitive client and structure. It's not one where it's easy to get a sample. And we unfortunately did not record the grout lot number. So what do? Well, certainly verifying that the grout lot is from Marion, Ohio is the first step. And ways to do that, potentially through submittals. or bag photos, which we did take some photos of the bags in this case. Unfortunately, they did not capture the grout lot number. So through neither of those possible sources of information do we have the grout lot number. Contractor records and where they bought it, and potentially follow the trail of where that person bought it from. It appears we might be able to get some information there to identify the grout lot number. And then the next possibility would be to try and cross-match the distributor or wherever the contractor got it from with Sika's records. Again, in this particular project, it sounds like the material was obtained directly from Sika, so I think we should be able to identify the grout lot number with a little digging, which is good. And the project location can also be helpful to identify if it's likely grout from Marion, Ohio. This particular project is in California, and most of the Marion, Ohio grout ended up in the Midwest or on the East Coast. Very little went to California and the western states. Also, the data work can bracket the expected chloride content as shown in the graph. If we're talking about a project from 2003 or 2004, in general, the chloride contents that have been both determined from field sampling and retains are lower, are not necessarily above the specified limit. However, this project was in 2009, where we found quite a bit of scatter in the chloride content data, and most of it was over the PTI specified limit of 0.08%. Other possible things to take a look at would be if there were any grouting problems, if there was anything noted with the material either during mixing or installation. On this project, there were none noted. Also, what is the risk level? If there is corrosion, what is the risk? And on this project, I believe epoxy-coated steel was used for the retrofitting as opposed to uncoated strand or uncoated steel. So even if the chloride content is high, for this particular project, the risk of corrosion would appear to be relatively low. However, at the end of the day, if you're concerned, the best way to know what you've got is to get a sample. And it's a little challenging on this project because it's a sensitive finish, sensitive project, and an owner we'd rather not ruffle feathers with, but it may be warranted given the circumstances. So I guess as I look at this project, I think it's probably not likely Marion, Ohio grout, but the first thing I would do is follow the product trail as far as I could to identify the grout lot number and verify that it does or does not end with an M. And if that doesn't go anywhere, or if it turns out it is Marion, Ohio grout, then I think it's probably warranted to approach the owner about getting in there and getting a sample despite the complications that go along with that. So at that point, Brian and I would like to thank you for your time. And there's certainly plenty of information that's available. Much of what was presented is available online, and we'd encourage you to read up on this issue and contact us if you have any questions. Thank you.